Welcome to the walkthrough for Assignment 1, Part B. The objectives of Part B of this assignment are to learn how to synchronize Java threads via a semaphore and a Spinlock. Videos describing Java semaphores appear on my YouTube page. There's also a video describing Spinlocks there as well. I recommend you watch all these videos to ensure you have a basic understanding of these Java synchronizers. Of course, we'll also cover these topics in class as well. In this part of the assignment, you'll use a semaphore and a Spinlock to enhance the multi-threaded implementation of the Palantiri simulator app that you began in Assignment 1A. Assignment 1B focuses on the Palantiri manager, which is an object that's used to restrict the number of beings from Middle-earth who can concurrently gaze into a fixed number of Palantiri. If you're not yet a fan of Tolkien's Lord of the Rings trilogy, you should drop everything you're doing and read about Palantiris here. The Palantiri Simulator app is packaged as a project in Android Studio version 3.x. The app itself is written in both Kotlin and Java and demonstrates many Android capabilities. For the purpose of Assignment 1B, however, you'll only need to be aware of the following three directories. The first is the manager's Palantiri Spinlock hash map, which contains the skeletons you need to fill in, as we talk about in just a minute. There's also an app source test directory, which contains a set of JUnit tests that exercise many Palantiri simulator features and can be used to help test the functionality you implement for this assignment to make sure it's correct. Finally, there's app source Android test, which is an Android Studio instrumentation test that can be used to run your app automatically. As before, you'll need to open the provided Android Studio project, and once it's open and synced properly, you can run the project by clicking the green Run App button in the Android Studio IDE, which will automatically prompt you for an Android emulator to run, assuming you've already created one and installed it. Once again, if you have any problems with this, please come to office hours and we'll help you get the Android emulator running. I'll also show you shortly how to run the various types of tests as well. There's a number of to-do tasks that you'll have to implement in order to complete Assignment 1B. Once again, please do not change the overall structure of the skeleton, just fill in the to-do tasks. In particular, you need to finish implementing the to-do task for this assignment in the Spinlock hash map folder. The two files you'll focus on are called Spinlock hashmapmanager.java for one, and you'll need to complete the to-do tasks in various methods and in the class itself in order to implement the Palantiri manager via a semaphore, a type of Spinlock, and a hash map. The second file you'll have to implement depends on whether you're a grad student or an undergrad. Undergraduates need to implement spinlock.java by completing the various to-do tasks in methods and in the class itself in order to emulate a compare and swap style Spinlock with so-called non-recursive semantics. In contrast, students taking the class for graduate credit have to implement something called the reentrant spinlock.java class, which I'll talk about in just a moment. After you finish those implementations, you go ahead and run your program, and again, it's considered correct if all the beings successfully complete all their n iterations. So a correct simulation should restrict the number of gazing beings to the number of Palantiri, so that if there's only 4 Palantiri configured in the simulation, then only 4 beings should ever be gazing at the screen at any given time. While the simulation runs, you'll be able to get visual feedback showing the states of the Palantiri and the beings, as well as the progress of the gazing that's taking place. If your implementation is correct and doesn't throw any exceptions, the title bar labels will appear as green when the simulation completes. However, if your implementation throws an exception or has problems with the implementation internally, when the simulation completes, the title bar labels will be displayed as red. Moreover, you should run the tests in order to be able to make sure that your implementation passes the unit and instrumentation tests. Graduate students have some additional tasks they have to take into account, or students who are taking the class for graduate credit have to take certain tasks into account. In particular, they need to implement the Spinlock hashmapmanager.java file to replace the Spinlock class with an implementation of the reentrant spinlock.java class, which emulates a compare and swap style Spinlock with so-called recursive semantics. We'll talk about that shortly. Undergrads are welcome to implement these features and methods, but it's not required. The skeleton code for this assignment can be downloaded from my GitHub account. Assuming that you've already set up your GitLab account, you can simply go ahead and pull the skeleton code into your repository, reading it carefully in the directories we've described, and completing the various to-do task markers. The additional work that the grad students need to do is clearly marked. This assignment is designed to help you get familiar with writing multi-threaded programs using the Android Studio IDE and core Java synchronization mechanisms. It is designed to complement the Java multi-threading mechanisms that we used in Assignment 1A. This assignment, however, doesn't require you to program any Android concurrency or communication frameworks, which we'll cover in upcoming assignments. Now that I've given you an overview of the assignment, let's drill down on the various skeletons you'll need to implement. These skeletons all reside in the Managers, Palantiri, Spinlock hash map folder. We'll start with the Spinlock hash map manager class, which everyone needs to implement. This class extends the Palantir manager and uses a Spinlock, a semaphore, and a hash map in order to be able to restrict access by many being threads to a fixed number of Palantiri. You'll have to provide a field that is used to implement the Spinlock. This Spinlock, in turn, will be used to ensure that threads serialize on the critical sections we'll look at below. There's two different Spinlock implementations. One, which is the Spinlock class, which undergrads have to implement, and the other is the reentrant Spinlock class, which students taking the class for grad credit have to implement. In either event, you need to define an instance of that here as a field. You'll also have to define a counting semaphore that limits the concurrent access to the fixed number of available Palantiri that are managed by the Palantir manager. I provided you an implementation of a Palantiri map, which is a hash map that associates the Palantiri key to a Boolean value that's used to keep track of whether the key is available. You'll see how that gets used in just a moment. There's a hook method called back called build model that's called by the framework. And this is used to initialize the various fields we just described. So we go ahead and make a new hash map. And then you'll have to call the getPalantiri factor method and use the result that comes back to that in order to be able to initialize the Palantiri map with the appropriate values. You'll also have to initialize the semaphore to use a fair implementation in order to mediate concurrent access to the given Palantiri. And finally, you'll have to implement the Spinlock field. So those are fairly straightforward things to do, but you have to think through how to implement a fair semaphore. That's probably the thing that'll take little doing. Down here is the acquire method. This method is called back in order to be able to acquire a Palantir, and it's intended to block until one is available if there isn't one available right away. So the way this works under the hood is you'll use the semaphore in order to uninterruptibly acquire a Palantir, or rather, let me rephrase that, in order to wait until there's a Palantir available. And then you'll use the Spinlock in order to ensure that only one thread at a time can actually come in and check the hash map to find the first key whose value is true. And this, of course, has to be done with the lock held so that you don't end up having race conditions when concurrent threads would update and access the hash map simultaneously. Once you found a free Palantir in the hash map, then you need to set its value to false to indicate that it is not available. And then that Palantir will be returned to the client and you'll release the Spinlock. All the code I just described needs to go here. There's also a little check, sort of a sanity check at the bottom of this method that will throw an illegal state exception if something went wrong. So make sure that you return properly, and if things go awry, make sure you go down here to throw this illegal state exception. Here's the release method. The release method is, of course, the inverse of acquire. It's intended to return the Palantir back to the Palantir manager, so it's available for other beings to use. And the way this works is the Palantir is passed back in. You'll need to be able to use the Spinlock in order to make sure you have exclusive access to the hash map. Go ahead and change the value in the hash map to set it to true, saying it's now available for reuse, and then you'll release the spin lock, and then you'll also go ahead and increment the semaphore to indicate that there's now a possibility for another thread to go ahead and get access into the Palantiri manager if there was a contention for the number of beings that were currently gazing with the limited number of Palantiri. So those are the methods that you have to go ahead and implement. Here's a little hint. I call the field M available Palantiri. That's just the name that I used. Up here, when I defined this, you could call it something different if you wanted to, but that was what I happened to call it. So probably wouldn't be a bad idea to use the same name. It's currently colored in red because I have taken that definition out, so you'll have the fun of figuring out how to do the implementation yourself. Let's go take a look at the skeleton for Spinlock. This is what the undergraduates have to implement. So the Spinlock is used to emulate a compare and swap style Spinlock with so-called non-recursive semantics. That means that once a thread acquires a lock, it cannot reacquire the lock unless it releases it first. The way you're going to do this is you're going to use something called an atomic Boolean, and that has a method called compare and set, and the default state of the Spinlock should be unlocked. So you'll have to go ahead and define an atomic Boolean with those properties set here. There's a method called try-lock, which is used to do a non-blocking acquire, so you'll have to go ahead and use the atomic Booleans compare and set method correctly here to do that check. The main method that you'll use is the one that's called lock. This is the one you have to implement. This is used to check to see whether or not the whether the lock is available, and if it's unlocked, then we're going to atomically lock it and then return. If it's already locked, we're going to continually spin, waiting for another thread to release that lock. So that's where you're going to have to use the atomic Boolean compare and set operation in order to do that. And there's a method, there's a field rather called mOwner, which is what I called the atomic Boolean. So I called it mOwner for lock owner. And this describes how you'll need to do this. You'll need to have a loop here that keeps trying to atomically set the value to true. And you should also, each time you try and fail, you should also check to see if a shutdown has been requested. And if it has been requested, then you want to go ahead and throw a cancellation exception. So you're going to check to see whether cancellation has been requested, and if so, it'll shut it down. Unlock will simply atomically set the Boolean to be false. In other words, it's now available for use. So you'll have to do an atomic operation. Of course, everything on the atomic Boolean is atomic, but you'll have to call the appropriate method to set the value of the lock to be false, which means it will be released. So we'll talk about how spin locks work in class, but these are basically the things you'll have to implement in order to make this work properly. Let's take a look at what the grad students have to do. The grad students have to implement a spin lock that has so-called recursive semantics, which we call reentrant. So a reentrant spin lock is like a spin lock, but it has this reentrant property. And all that means is that if a thread currently owns the lock, then it can reacquire the lock, simply incrementing a recursion count without having to release it first. So it makes it recursive. So basically, what you're going to have to do here is define an atomic reference that's used as the basis for the atomic compare and swap. And the default state of the spin lock, of course, should be unlocked. Now, the way you're going to do this is we're going to actually keep track of the thread ID that's the current owner of the lock. And so you'll have an atomic reference that's parameterized by thread. You'll also have to define a field that will count the number of times the owner thread has recursively acquired the lock. And so it just has to be a simple count, nothing fancy here. You can use an int, for example, as long as you give it the right default value. Over here, you have to implement the try-lock method. This is the one that's used for non-blocking acquisition of the lock. And what you'll have to do there is fill in the value to basically try to set the owner's value, which this is the owner of the reference, to the value of the thread, which is considered true. And this will succeed if and only if the current value is null, which indicates false. So that's just sort of a one-liner. Down here is really the workhorse method. This is the lock method. Similar to the one that the undergrads have to implement, the main difference here is that you'll have to get the current thread, and then you'll use the thread reference in order to be able to try to set the value of the atomic reference to the current thread reference. And that thread reference, of course, will be non-null. And so you'll have to keep checking to see whether or not you can atomically do compare and set to set the value of the atomic reference to the thread reference, and then check to see whether it's null. So you'll have to figure out how to do that. Once again, you'll have to check each time you fail to do the set atomically, when you fail to get the exclusive access, to check to see if you've been canceled or not. And then if you haven't canceled, you have to throw a cancellation exception. Unlock simply goes ahead and sets the value back to null, the value of M owner, which is the atomic reference, back to null, but only if the recursion count is going to be equal to 0. If the recursion count is greater than 0 and the calling thread, the thread that calls on lock, is the one that currently owns the lock, then simply the recursion count is decremented by 1. So only when the count is 0 and the calling thread is the thread that owns the lock will we atomically release the lock that's currently held by the owner. So those are the various classes you'll have to implement in order to be able to do this part of the assignment. The key thing you'll be learning here again are semaphores in order to be able to mediate access to shared resources concurrently, as well as spinlocks, which are used to guard critical sections from simultaneous access in order to be able to prevent race conditions. Now that we've walked through the skeletons you'll have to implement, let me show you how to run the unit test. If you go over to your IDE in the left panel and you go into the test folder, you'll see that there's tests in here called Managers, Beings, Runnable Threads. If you simply right-click on this, you'll get a menu item that says Run Tests in Runnable Threads. If you click on that, it'll bring up a window, and you can see then it goes ahead and it runs a bunch of JUnit tests. And these JUnit tests go and test various aspects of your implementation. You can see here that they run the simulation, they test the beings, they test various other kinds of aspects of the way in which the program is supposed to work. So naturally, you want to go ahead and run those tests in order to see whether your program is working properly. If all the tests work correctly, then everything will be green, and you can go ahead and it'll give you little results saying things run properly and so on. If something fails, then you'll get red or yellow, and then the errors will appear in the window here, and so you can see, hopefully, a better insight as to what is going wrong in your code. The last set of tests I want to show you to use are called the instrumentation tests. If you go over here to Android Test, and you right-click here, it says Run Tests in EDU Vandy. It will then prompt you to pick this emulator to use, and the emulator should pop up, which will go ahead and run the Gradle build. And then you can see what happens is it goes ahead and it automatically launches the emulator and begins to run a number of different tests. You can see here what it's doing. It's basically going through the tests, checking to see whether or not the implementation you have work, using some torture tests to run with 10 beings and 6 Palantiri for 10 iterations each, and it keeps track of whether or not the tests are completing. As you can see, if it all works properly as it is here, everything is green, and then it goes ahead and starts everything over again, runs a bunch of new tests. So there's different things that are being exercised, different capabilities that are being exercised through each of the tests. And you can see also that this is running in so-called performance mode, which is not putting any delays between the various runs of the beings accessing the various Palantiri. Now, as you can see here, everything passed correctly. It's all a bunch of green. And so this is a good indication that our program actually worked properly. If you run these instrumentation tests and things go wrong, then it will hang, probably turn red. You'll see all kinds of errors hopefully coming by. And you should also be able to go and look at the logcat output, which is what's generated here And then that will also provide you logging output to indicate what may be going wrong with your tests. So hopefully this will give you some indications on how to run the tests in order to be able to take a look at the output. And again, if everything goes well, you should get nice green results. If things go wrong, you'll get red, and hopefully you'll be able to see why things went awry. We will also be using these tests to grade your final submissions, so make sure that everything is passing before you go ahead and submit your code.